Okay, everyone, sorry running a little late. Today I just plan on doing just reviewing for the exam. Any issues with the lab? Everyone have it done? Yes.
There's no submission.
Oh, right, yes, thank you. I'll do that right after class. Thank you. Yes.
If we, well, I guess now since we don't have another lab period, do you want to, like, for the demo portion, can we, like, submit a video of it?
Sure. Yep, that's no problem. Yeah, videos are fine. Or we could meet outside of class. That works too. Or you can meet with, schedule a time with Phil to meet outside of class. Okay, so we had I think we had a quiz due on Sunday, I think, the real-time scheduling quiz. So I'll go over that real quick, and then I'll double back and go back to the beginning of the semester and kind of run through all the topics we covered, since the final exam will be comprehensive. Okay, so the quiz first question said, assume four tasks with execution time period values of 415, 420, 625, and 730. What is the utilization? For this, you just add up the ratios of execution time in periods. So this would be 415s plus 520s plus 625s plus 730s is 99%. Assume four tasks with execution time period values of, same thing. What's the RMS bound? So the RMS bound, there's actually more than one RMS bound. I think the one that I presented in class is the latest one. And the idea is that you for each task, you multiply 1 plus the ratio of execution time over a period. So you multiply those up, and if the product is less than or equal to 2, then it's guaranteed to be schedulable. If that's not the case, then it may or may not be schedulable. So the RMS bound is the product, and so in this case you just take 1 plus 4 over 15 times 1 plus 5 over 20 times 1 plus 6 over 25 times 1 plus 7 over 30, and that's 2.42, so that is greater than 2, so there's no guarantee that those tasks will be schedulable. Now, one question I might ask on the exam is, if the tasks don't meet the criteria defined by the bound for being schedulable, we don't know if they're schedulable or not. But one way to know for sure if they're not schedulable is how? How would you know for sure they're not? You guys know?
It's more than 100% of your processing time.
Exactly, the utilization. Yeah, you can calculate the RMS bound and the utilization. Now, if the utilization is less than 100%, but you don't meet the bound, then it's really kind of uncertain. But if the utilization is greater than 100%, then there's no way you could possibly schedule these on one processor. That makes sense? Okay. Okay, assume 3 tasks with execution time period values of 210, 720, and 2540. Are they schedulable with RMS? So we calculate the bound, 2.63, probably not schedulable, although we don't know for sure. Now the utilization, this is just what I was saying, is that the bound was 2.63, utilization is over 100%, so they're definitely not schedulable. Okay, assume 4 tasks, 1, 2, 3, 4, with execution time period values of 2, 5, 4, 7, 3, 11, and 4, 12, and 2 processors. Are they schedulable using partitioned RMS scheduling? If so, which task processor assignment is schedulable? Okay, so this one, I didn't talk a lot about this one in class. Partition is when you just assign tasks to a processor separately, and then you do RMS scheduling on each processor. The problem is that there's lots of ways that you can assign processes to processors, although in this case, there's only 2 processors and 4 tasks, so it's not too bad, right? Makes sense, right? I don't know why that's glitched, but yeah, there's 2 to the 4th power assignments. Is that right? Is it 4? Wait, no, I'm not reading that right. Hold on. Yeah, 2 to the 4th power. Yeah, that's right. Yeah. Okay. So now I say that, so 2 to the 4th power, because you essentially have, you could think of this as having 4 symbols where each symbol has an alphabet size of 2. You know, you have to pick one process or the other. So it's 2 to the 4th power. Half are redundant though, because, you know, obviously if you put like all tasks on processor 1, or half the tasks on processor 1 and the other half on processor 2, that's equivalent to just, you know, swapping the 2 processors, right? So let's see, 2 to the 4th power is 16. Half of that is 16. Sorry, half of those are 8. Yeah, so half of those 8. So I list the first 8 here. These other ones here are duplicates of ones above. So in this case, I gave a full enumeration of every way to do the mapping. And so, you know, I could map tasks 1, 2, 3, and 4 to processor 1 and nothing to processor 2, but that violates the Rms bound. I didn't calculate the utilization for these, probably should have, but what I'm looking for is just a way to assign the tasks to processors where they meet the bound, right? And so that actually happens down here, where I put task 1 and 4 on processor 1 and 2 and 3 on processor 2, in which case I get 1.87 and 2 for the Rms bounds, right? So that looks good. I don't think there's any other way to do it. I think that's the only solution here. Does that make sense? So I just kind of brute force this. Assume 3 tasks, 310, 411, 412. Under which algorithms are they schedulable? So with EDF, as long as the utilization is less than or equal to 100%, then you can schedule with EDF. EDF, as I mentioned, though, is really nice in terms of being able to schedule anything that's physically schedulable, except that it's very expensive to implement. Because the priorities of the tasks are dynamic and they're constantly changing. You have to do a lot of priority recalculations. So now with RMS, we calculate the RMS bound. It's 2.36. You know, probably not schedulable with RMS. And I guess, yeah, it's only 2 options there. Okay, assume 4 tasks, 319, 420, 521, n22. What's the largest value of n that would make the task schedulable with rate monotonic first fit scheduling on 2 processors? Now, rate monotonic is basically just a fixed utilization. So that one's really easy. In fact, I think it's even easier to calculate the rate monotonic RMS than it is for regular RMS, because all you have to do is take the square root of 2 minus 1, which is about 4.41 or so, and then multiply that by the number of processors, and that's your utilization bound. So in this case, I just you know, solve for n here, and n is must be less than or equal to 5.11, so the answer there is 5, because I didn't say it explicitly, but I guess I didn't say this, but it was kind of implied that the execution times are integers. And of course, the quiz was, you know, multiple choice, so 5 would have been the closest answer. Okay, so 4 tasks, 2.8, 5.12, 6.16, 7.20, are they schedulable with EDF on 2 processors? Now this one is a little strange. So the first condition is the utilization has to be less than the number of processors, which is 2, which is the case, it's 1.39. The second condition is kind of strange. You have to calculate the least common divisor of the periods, which in this case is 8, 12, 16, and 20, so it's 4. Okay, and then you multiply that greatest common divisor against the rate for each task. You multiply the greatest common divisor of the periods times the ratio of execution time over period, and you're looking for that number to be an integer for all the tasks. In this case, for the first task, we have 2/8 multiplied by 4 is 1. But then the second task is 5/12 multiplied by the greatest common divisor of the periods, which is 4. And you end up with a fractional number, so you can't, that disqualifies it. That basically fails the test. It fails the test that would guarantee that they're schedulable. Okay, how many possible ways can 5 non-periodic tasks, now non-periodic meaning they run once, be scheduled assuming they're all ready? 5 factorial. Which statement is true? RMS requires static priority. That's true, right? What is the static priority of RMS? It's the period, right? RMS requires dynamic priority, not true. EDF and RMS require static priority, not true because EDF is dynamic. EDF requires static priority, no. So it's the first one. Which statement is true? Any task that can be scheduled with RMS can be scheduled with EDF. Yeah, I think that's true, yeah. Yeah, if you have one task set, if you can schedule it with RMS, then that means that it is scheduling with RMS is more stringent than EDF, so that should be true, right? Yeah. Okay, yeah, any task that can be scheduled with EDF can be scheduled with RMS, not true. Any task having utilization that meets EDF bound will also meet the RMS bound, no. Any task that can be scheduled on the 2 processors can be scheduled on 1 processor. This one, I don't know if I have an example. Let's see if I could find an example of that. Oh, 2 processors can be scheduled. Well, I'm sorry, I thought it was the reverse. Yeah, any task set that can be scheduled on 2 can't necessarily be scheduled on 1 because you can schedule a task set with more than 100% utilization if you have two processors, right? Yeah, that's the idea there. Okay. All right, that's it. Any questions? Okay, so as I mentioned, the final exam is comprehensive. It'll be on Friday. 25 questions. It's going to be, it's going to cover everything. So I'm just going to quickly run through the lectures, and if you have any questions, let me know. I'll get through this. Hopefully, I'll be able to get through this kind of fast, and we can, let you out a little early today. Yes.
Do we have 2.5 hours?
Yes, I believe so. Is that what I said?
I don't know.
Let me double check that. I had it in the lecture 5 slides here, right? Oh, I guess not. I believe so, yeah. Yeah, but if not, I'll send you an email. Okay. 150 minutes. Yeah, I think that's, 2.5 hours. Yeah. Okay, so going way back to the beginning of the semester, we talked about interfacing. And hopefully you guys are pretty comfortable with this because we use this quite a bit in the labs, this idea of writing to memory addresses in order to exchange data between a CPU and peripherals. So you can calculate, peripherals have, one of the things though that we didn't do in the lab is interact with a peripheral that has more than one word of I/O space, right? Every peripheral you guys access was one word. There was just one value, like the keys, the LEDs, well, actually that's not true. The performance counters were an exception to that. There were 2 words there, right? There was a offset 0 and offset 4, right? So yeah, there was one case where there was multiple words. Some peripherals could have a pretty big address space though. They could have, hundreds of different locations that you can write inside a peripheral. We just never used any in this class in the lab. So there's an address range associated with peripherals. So I/O registers, or some people call them control and status registers, are that's the term that's used to designate the addresses that you're writing and reading into for the peripherals. And we talked about bit twiddling. This is manipulating individual bits. Make sure you remember how to do this. It's essentially just using a combination of bitwise ands, ors, and shifts. So this way you guys finally get to really use those for something after having learned them in 212, right? So if you want to set bit 2 in a register, there's one way to do it is to just take the value 1, shift it 2 bits to the left, and then do an OR, right? Is there another way to do that? I don't know how else you could do that. I'm not sure how else you'd do that, actually. You don't have to set it to 1 and shift it. You could also just set this value to 100. What's that? 4, right? Yeah, you could just set it to 4. But the problem with that is that if the bit value you're setting is not known until runtime, right, then you would want to have a shift amount that's a variable, right? If you know what the position is, then you could just hard code it, as a 4, which is 2 to the second power. Right? Clearing a bit is just a little bit more complicated. You have to use a bitwise and in this case, you have to shift the bit that you want to clear and then do a bitwise complement, which is a tilde, and then do an and. So that'll clear a bit, leaving the other bits intact. Isolating bits can be done through shifting and anding. So this shifting is not necessarily needed depending on what you want to do with the bit. But assuming you want to get the bit that you're trying to isolate out of the register into the right bit, get it to the right-hand side, then you would shift it, in this case, 3 bits to the right because it's in bit position 3, right? So 0, 1, 2, 3, so we shift it 1, 2, 3 bits to the right, and then use this bit mask to sort of just clear off all the other bits. Make sense? Okay. All right. So let's see. If there's a range of bits, it's the same thing. The only difference is the shift amount is the lower end of the range, and then when you do your mask, you have to make sure that there's multiple bits in the mask, and you mask off the bits. Okay. All right. So that's summarized there. Okay, then we talked about pulse width modulation. Of course, you guys use this quite a bit in lab. I think we use this in labs 2, 3, and 4. And this is, just setting the duty cycle. Now, by the way, have any of you guys tried using lower frequencies for the PWM? So we've generally tried to target about 10 kilohertz, right, where we switch this thing at 10 kilohertz, right, and then set the duty cycle. But is that too fast or too slow? Is there any advantage of going faster? Yes?
We experimented with making the frequency greater, like making the period smaller, and found that the motor didn't really work with that. Anything much faster than 10 kilohertz, it didn't seem like either it could respond or something like that.
That's interesting. I hadn't tried anything faster. Kind of surprised that it doesn't work. It's faster, but it could have to do with the H bridge and how fast it can switch internally. Anyway, one of the projects I always wanted to do in this class was to use pulse width modulation for audio, to have it play a song, like set the PWM duty cycle to be an audio signal, right? That would be pretty neat. I never got to do that though. My understanding is that that's how those greeting cards work, by the way. At the grocery store, those greeting cards that play a song, they're actually just using raw PWM into a speaker. Okay, so interrupts. We didn't program any interrupts on the Neos. We could have, but we didn't. We probably should have. Just didn't have enough time to do that. The Neos has, I believe it has an acknowledgement system. Although you guys did connect interrupts inside SOPC Builder, right? At least for the Uart, but you didn't use them. Can anyone think of what the interrupts would be used for with the Uart? Like why we need that?
If you like interrupt a download.
I think the interrupt is only used for input. Like if you type something in the terminal, right? Like everything you guys have done was output, right? You printed messages, but if you wanted to accept an input and you wanted to say like press any key to continue, I think you could hit, when the user hits a key, that would trigger an interrupt potentially. But I haven't tried that. Haven't done a lot with the terminals and with the Neos. Okay, so we've got, we talked about, if you have any questions, let me know. I'm gonna kind of cruise through this. Then we got into bus protocols. SPI and I2C are obviously pretty primitive, low-level, slow protocols, but they are still used. I mean, you've got them like on your motherboard to this day. There's I2C and SPI channels. I think the PCI bus has a side channel that's I2C for debug. So they're pretty common, but they're not, obviously they're not intended to be high performance. So we've got synchronous versus asynchronous. That basically means if there's a clock signal. SPI is single master, I2C is multi-master. You guys remember the Avalon bus that you used in the hardware, right? We didn't talk too much about that. You guys did interact with it in a simple way with the Lab 3. But Avalon is what's the difference between Avalon and I2C and SPI? Avalon is a parallel bus, not serial. So when you guys respond to the Avalon request in Lab 3, those bits come in parallel, right? So the address and the data comes in all together. You don't have to do a serial to parallel converter as you do with these protocols. Okay, so why would we choose a parallel bus over a serial bus? What's the deal? What's the advantage? Well, parallel buses require multiple wires. And that's a lot easier to do on a chip or on an FPGA than it would be like on a circuit board. Because if you put multiple wires on a circuit board, it's very difficult to have all the bits arrive at the same time. Because the wires are usually different lengths because you have to route them as a bus, right? So also there's a lot of capacitance between the wires and crosstalk. It's kind of nasty, which is why PCI Express and DVI and HDMI and DisplayPort and SATA, they're all serial. They're all serial. Everyone's gone to serial. Even the high-speed buses are now serial, right? The chip-to-chip buses anyway, right? They've all gone serial just because it's easier to deal with serial. And by the way, the serial buses that make up like say HDMI are they're differential, meaning that instead of 1 bit per wire, there's 2 wires per bit, and the wires switch polarity relative to one another, kind of like how the H-bridge does, switches the polarity. And the reason for that is when the wire picks up noise on the wire, it picks the noise up on both wires, and when you subtract them, it cancels it out. It's called common mode noise rejection. Anyway, yeah, but SPI and I2C are single-ended, obviously 1 wire per bit. Serial, SPI has those 4 modes that we talked about, CPUL and CFA, kind of pointless, I think, but for whatever reason, it's kind of part of the protocol. So CFA was clock phase, what the clock is by, when the bus is inactive. And, C-pole, that was C-pole. C-pole was the polarity of the clock, and CFA was the edge of clock versus SS? CFA? Yeah. So clock, edge, SS edge is offset, right? Whereas when CFA is 1, not clock, scratch that. SS versus data, that's what it is, right? The data. So SS and data are lined up here. They both change at the same time, right? Whereas over here, the clock and the data are offset. So CFA of 1 is where you push the phase of the data out relative to the clock. Make sense? All right. Okay, then we talked about exchange. So there's exchanges versus transactions. The transaction is when you have to do multiple exchanges, because I don't know what SPI was originally intended for, but obviously, when you do these kind of transactions, you want to be able to send an address to your slave, right? To tell them what you want to do. So in order to implement that with SPI, you need multiple transactions. You guys all remember that? Okay. All right. So then we get to I squared C, and we talked about, Uart first. So Uart was really simple. It's got basically just one bit. There's one bit for transmit, one bit for receive. There's virtually there's no control wires here at all, just data wires. The control information is encoded on those wires serially through the start bit, the parity bit, and the stop bit. But it's an asynchronous bus, so both sides kind of have to have their own internal clocks that synchronize according to the baud rate, where they both have to agree on the baud rate, right? So the downside here is that Uart is much slower than I squared C and SPI. Those are faster protocols. But it's fast enough for dumping the log file out from Lab 4, right? That's the idea with Uart. The one thing that's confusing about that, at least in my opinion, is the parity bit. The parity bit is a little non-intuitive, because if you have a even parity, that means that you are supposed to have an odd number of 1 bits set in the data, right? Because then the parity bit would then be high, which would be an even number of bits set in total, right, across the data and the parity bit. All right. Okay, then we talked about Uart, or we talked about the push-pull versus the open-drain interface. The objective of the open drain is just mainly for protection when allowing multiple devices to drive the same wire, right? So that's needed for multi-mastership. Unless you have these tri-state buffers. So why, if you got tri-state buffers, then why would we want open drain? Well, I mean, tri-state buffers still have the disadvantages of if you screw up, you can still cause a catastrophic failure, right? If the tri-state buffers aren't all synced up properly, right? Like if 2 of them try to drive the wire at once. So open drain is just safer. It's a safer way to go for multi-master buses. Excuse me. Okay, so I squared C. The confusing thing here is that this is not an edge-based. This is not an edge-based protocol, right? This is based on levels, right? So the data is sent when the clock is high. And you're not supposed to change the data when the clock is high. And so the whole architecture is based around that concept. And the only time you do change the data when the clock is high is when you're signaling a start or a stop. You guys remember that? So that's really the only thing. I think that's the most important thing to remember there. The other thing that's a little strange is that the clock is always controlled by the master, right? Yeah. The data is handed off back and forth, right, during a transaction. So it starts out in the master's control, and then it goes to the slave, and then back to the master, and then the slave, right? And then there's this acknowledgement bit for both the data and the address and the data section. One thing that's kind of cool about I2C is that the clock is controlled by the master, but remember that because of the open drain design, technically the slave could prevent the master from raising this. Remember that, like, if you don't do anything with open drain, the signal is logical high, but if either side were to pull it down to 0, it's going to stay at 0, regardless of what the other side wants, right? It gives you a way to wrestle control of something away from someone else. The way they use that in I2C is they have this idea of called clock stretching, where the slave can drive the clock low, even though it's not supposed to be messing with the clock, but it can do that in order to prolong a transaction if it needs more time, right? So we didn't talk too much about that, but that's kind of a neat feature, I think, of I2C. Okay, and then Jtag. Jtag is also a serial protocol. It's kind of like SPI in that it's a big shift register. The important difference with Jtag is this TMS input, test mode select. Test mode select is a control bit that allows you to put every device on the Jtag chain, the chain being, linking these guys up, TDO to TDI to TDO to TDI. You can put these devices into a specific mode, right? You could put it into an address mode or a data mode, right? The address mode is where you set the address. The data mode is where you read and write the data, right? And that happens through a sequence of bits that comes in through TMS. How long is that sequence? Well, it actually varies. It depends on it depends on what you're trying to do. So if I want to put data in, I have to find a path to data. So I have to go 0, 1, 0, 0, 0, 1, 0, 0. So in 4 cycles, I can get to the data register state where I'm putting stuff in, where the test data out is sending data into the data register. Make sense? Okay. All right. That's it for interfacing. Any questions? All right. Let's jump to the next topic here, which was what did we cover next? System Verilog. Yeah, I guess that was System Verilog was next. Oh, FPGA design actually too. So this was just a tutorial actually for the labs. Yeah, then we switched to System Verilog. By the way, you guys, how many of you have taken 611? Anyone? Oh wow, a lot. Okay, so you guys are pretty comfortable with Verilog then, right? Yeah, good. Okay. Well, that explains why the labs went so smoothly. I'm glad. I thought the labs went pretty smoothly this semester, so that's good. So, yeah, System Verilog is there's there's a subset of system Verilog that's synthesizable, meaning that you can compile it to hardware, right? But then there's this huge part of it that is non-synthesizable and is designed for testing, writing kind of arbitrary programs, right? I actually don't know much about that stuff. I mostly deal with the synthesizable Verilog, right? Which is nice because it kind of limits it to a fairly simple language if you're only talking about what you can convert to hardware. It's basically just a sign statement, structural Verilog, and the always, right? That's pretty much it. And so that's what we focused on in this class. So we talked about how you set up a module. This is just basically syntax. Make sure you got the semicolon at the end of the module statement. And we talked about assign statements. Structural versus behavioral. Structural is schematics, right? Interconnections, instantiating modules. Behavioral is assign and always statements. We talked about how Verilog is has 4 states, which is not enough for me because I like VHDL. VHDL has I think 6 states for each bit. So Verilog has 1 and 0, but it's got also Z, high impedance, meaning that the signal's not connected to anything, no one's driving it, and X. The problem is X, because X can mean a lot of things. X could mean conflict, signals in conflict. It could mean that signal's undefined because it's coming out of a RAM or a register that hasn't been initialized. Could mean don't care. If you're setting a don't care in your design, you can set a signal to X, right? Well, that's terrible. Why not have separate values for that stuff, which VHDL does. VHDL don't care is a dash, a hyphen. And undefined is a U, meaning not initialized. And contention is an X, right? So VHDL has 6 states, Verilog only has 4, but if you use Verilator, which is a really popular thing right now where you can compile Verilog and actually run it on a computer, on a Linux machine, then you only get 2 states. So if you have any weird things in your design that would be caught normally by finding X's, you're in trouble because you're not going to find them. So that's why we were using Verilator in this class actually last time I taught it last spring, but the students didn't like it. I don't like it. I like ModelSim and just running it on the FPGA better. Okay. Anyway, so let's see. We had some examples here. We talked about design hierarchy. This design hierarchy, you might look at that and say, well, just, that's obvious. But it's actually, I found that when you do large-scale designs, it's actually tricky how to decide what to put in a module or not. Like, how do you know, because you can build this huge module and have everything in there, or you can break it into 20 different submodules. What do you do? Well, whenever you're designing something like that, the question you should ask is, if you break something into a submodule, is there a chance you can reuse it for something else? And if the answer is yes, then you definitely want to have it in its own submodule, because this exploits the idea of regularity. Regularity is just like, I've got a module and I can reuse it a lot. That's regularity. And if you can, that's great, because then you end up having very few lines of code written and 1 billion transistors in your chip, right? That's what you want. Because you don't want to have to debug a lot of code, you don't want to have to write a lot of code, but you still want massive chips with 1 billion transistors, right? And so by exploiting regularity, you can get a high degree of reuse out of these modules, and you can create arrays of them like you did in Lab 3, where we created an array of modules, for the PWM. I thought that was pretty cool with the generate statement. So you didn't have to write a lot of code, yet you got a lot of transistors in there. You got a lot of logic. Relatively for the amount of code you had to write. Okay, so modules, we talked about modules, and we talked about simulating, but you guys never got a chance to do this in this class, but I think most of you took 611, so you have done it in 611. Instead, we used Jtag. We used, you were supposed to, I don't know how many of you guys actually did it, but I showed you how to use Signal Tap, which allows you to debug live designs. I think that's, it's nice to be able to do that. The problem is, it's like you do it and you're like, oh, I want to add another probe, and then you have to recompile. That's a problem. But so we talked about how to read those things, timing diagrams, always statement. Are you guys comfortable with the always statement? Kind of, a little bit. So the idea is that you just want to write complex code, like you want to write code like you would in software, but you want to do it in an HDL, and that's what an always statement is for, basically. It's just a complicated block of code. It allows you to use if statements and stuff. I try not to use always statements for combinational logic. The only exception to that is the control unit in 611. You guys remember that? The big, huge if-then-else statement to control your CPU. I wouldn't want to do that with an always, or sorry, with an assign, rather. Okay. All right, structural Verilog. We talked about hierarchy, how to connect stuff. Operators, bit manipulations. I think I assume everyone's okay with this, right? You can concatenate bits and replicate bits. Yeah, that's about it. Generate statement, you guys use that for the lab. FPGAs, Signal Tap. Okay, good. Signal Tap stuff was mostly just for your use in the lab. I'm not going to ask you about Signal Tap or even the FPGA tools on the exam. I'll ask questions about Verilog, but nothing specific to the lab stuff, because that was just for for the lab work. All right, control theory. Okay, so control theory is a little bit outside of our discipline, frankly. It's taught in electrical engineering and mechanical engineering. But it's relevant for this class because this class is about designing computers to control stuff, cyber physical systems. And so I wanted to kind of give you an introduction to control theory. Frankly, I'm not an expert. I just know the basic stuff. So we've got, obviously the open loop versus closed loop control. And we talked about linear time invariant systems. This is confusing, by the way. Linear time invariant, like, okay, you have a linear time invariant system, right? Right. Oh, I'm going to put a sine wave in. But a sine wave isn't linear. Oh yeah, well it's linear, but it's linear in the sense of differential equations. It's like, okay, so that's really what it's talking about, is that it's linear in the sense that you're multiplying only coefficients times derivative and integral terms of a time series signal, right? So that's what's meant by linear time invariant systems. The strange thing about this is that you might say, well, wait a minute, like, can you do nonlinear time invariant systems? Is that possible? They exist, but there's no good ways to do analysis and design with nonlinear systems. Like, all this S-domain stuff that we're doing is designed for these linear LTIs, right? Now, you might say, well, wait a second, the motor design from Lab 4, is that linear? Is that an LTI? It has a linear operating range, yes. But the problem is that the fact that you can max out the motor and it just stops going faster, that's a nonlinearity, right? But normally when you design for something like that, you just design it for the linear operating range of the system, which is that range that's sort of in between the two extremes, right? Okay. So, so we talked about some examples of converting between time domain and S domain. S is a complex number, and S is comprised of two parts, the steady state and the transient part, but we didn't really get into that. We just treat S as we just say, it's just for the purpose of being the variable when you go to the S domain. So what do we want to know with this? What are we doing with this? Well, we're figuring out, one, if we have a stable system. So if you have an LTI, we can determine whether it's stable or unstable. Sometimes people want to know that, right? Normally, when you control something, you assume that the system as a whole is stable, even if the thing that you're controlling by itself is not stable, right? Stability, you can determine if something's stability by hitting it with an impulse or a step function. Why? Why does that determine stability? What is special about the impulse or the step function? Well, the step function and the impulse is an instantaneous change in input, right? And so what's unique about these is that in order to construct either an impulse or a step by adding sinusoids together, it would take an infinite number of sinusoids to add together to create that shape. So really what you're asking when you do an impulse or step is how the system responds to every frequency. Right? That's really what you're asking, what you're doing there. Okay, so the impulse response is actually the inverse Laplace transform. So we talked about how when you do that, you can calculate the inverse Laplace transform. Right. The impulse. Sorry, let me back up here a second. Another way to tell if a system is stable is by finding the poles. Poles are values of S that create a divide by zero in the transfer function. Right? If those poles are in the left-hand plane, meaning that the real components of those are negative, then it's stable. If all the poles are in the left-hand plane, right? If even one pole is not in the left-hand plane, meaning it's zero or positive, then the system is unstable. That's an unstable LTI. Now, there's also a concept of zeros. Zeros are values of S that give you a zero in the numerator. What do the zeros represent? Well, the zeros define the behavior. By knowing the zeros, you can kind of determine characteristics about the transfer function in terms of its frequency response. But we don't care about that in this class. We just care about the poles because we only care about stability. Right? Sorry. Okay. All right. And then we talked about the inverse Laplace transform. It gives you the impulse response. And that's a way that's basically a way to derive the impulse response by hand. If you can find the eigenfunctions. Normally, the way you would find the impulse response is through a simulation. You might say, wait a minute, you tell me there's no other way to find the impulse response just by hand? I don't think so. Because generally speaking, if you have a system in the S domain, you put in MATLAB and you simulate, and it does a simulation, right? It simulates the differential equation, right? Instead of solving it, it simulates it, right? It kind of iterates through it, right? To figure out, starts with the initial conditions and then it marches through, right? But if you want to solve to find the impulse response, the only way I know to do that is through the the inverse Laplace transform. Okay, transfer functions is when you just multiply the LTIs together, and we talked about building a physical system model. Here's the problem with this, by the way. What happens if you build a physical system model based on first principles, and then you design a controller for it, and you run it in simulation, it works, but then you go to deploy it in the field and you find out that the system the plant, it doesn't exactly match what you designed it as, the model. See, in this case, we designed a model for this physical system, but what happens if the model doesn't match reality? Well, then you just hope that your controller works, basically. And if it doesn't, you got to go back and try to adjust it or make a more more accurate model, right? This was the question that we would have looked at in lab 5, is we would have taken the motor and developed a model for it, and then designed a controller for it, and then tried to deploy that motor on the controller on the actual motor, right? See if it worked, right? Okay. Closed loop control is actually super easy. I went through the derivation of it here, but basically all you have to remember is it's the open loop transfer function divided by 1 plus the open loop transfer function. Assuming it's arranged, with in this arrangement where you're feeding the controller with the difference between the set point and the output of the plant. I'm sure there's other ways you could arrange these blocks, but this is the kind of the traditional way that you would do it for something like a robot control or cruise control or something like that. All right, and then we talked about PID control. And then finally, and I think you guys are familiar, you seem comfortable with that from robotics, so you've seen that before. You can tune a PID controller. And then we talked about the Z domain. This is probably new. I don't know if you guys have seen this before. So the Z domain is the discrete form of the S domain. It turns out that you can't really deploy an S domain anything on a computer. It's impossible because computers are discrete. So the Z domain is a discrete form of the S domain, but for some reason it's kind of I don't know. It's like not as well understood, because like when it comes to stability, the stability criteria for Z domain is a little sketchy, right? Like for example, if you have poles that are on the unit circle, it may or may not be stable. We don't know. So it's not as cut and dry as the S domain when it comes to stability. But what I think is neat about the Z domain is that you can convert S domain to Z domain. There's multiple ways to do that. As far as I know, the most accurate way to do it is through the Tustin transform. The Tustin transform is where you replace S with this, which is nice, except the problem is that the math here gets really complicated really fast. If you have a big S domain transfer function and you do the Tustin transform, it gets overwhelming. It just blows up. Which is why people generally don't do this stuff by hand. They use tools like MATLAB to do this. But it's important to understand, what's going on and how they work. Okay, and I think that was the last topic. Oh, one final thing is, one other cool thing about the Z domain is when you go from the Z domain to the time domain, that's the cool part, because it's actually relatively straightforward to go from Z domain to time domain. Unlike the Laplace domain, it's relatively straightforward. The trick is if you can take your transfer function and get it into a form where all of the exponents to z's are less than or equal to 0, right? Then you can just basically, anytime you have a z with a negative exponent multiplied by a z domain variable, that just translates in the time domain as the value of that signal one sample ago if it's -1, or 2 samples ago if it's -2, and so on, right? How cool is that? I think that's neat, right? So you can translate this directly to u of t minus 1, for instance, where this is an array of samples, right? And t is the current sample, right? Okay, so all right, that's it for that. And then I think the last topic was real-time scheduling, which we just got done going over the quiz. One thing I didn't mention in the quiz is this idea of worst-case execution time. Yeah, there's really no way to tell. There's really no way to tell how long a task takes to run on a CPU. It's just. In modern operating systems like Linux, not only do they make no guarantees about how long it's going to take to run a task, But there's no way to even tell Linux how long you want it to run in. You can't tell Linux, run this program and try to do it in like 10 milliseconds. No, Linux is like, no, not accepting that. Not doing it. You can give priority levels in Linux, like you could set a task to high priority, but you can't even like suggest, like, there's no way to give it a deadline, right? So that's not good. If you have any kind of control system, right, you need to be able to meet deadlines. So you need to be able to keep the control surfaces on your airplane up to date, or you'll crash, right? So you can't be having a computer that doesn't give you any kind of guarantees on execution time. That's totally unacceptable. So how do you calculate worst case execution time for a task on a CPU? You can't. Basically, you can. The only way to do it really is to statistically sample it, run it a bunch of times, and calculate an average, essentially, right? Or you could run it like in a simulator, try to figure out. The problem is that code can be very complex. There could be different paths through it. It could behave radically different depending on what inputs you give to it. Not only that, but you have hardware things like cache and page tables and interrupts, and it's really hard to tell. So this was a very simplified statistical method I presented to you, where you just run multiple times, you calculate the standard deviation and the mean, and from that you can calculate a worst case execution time within a certain confidence interval, right? Based on how many standard deviations away from the mean that you go. Assuming that it's a normal distribution, which there's not even any guarantee of that, right, really. But I assume that was the case here, although in this example there was actually two normal distributions superimposed on top of one another. And when we treated them as two separate ones, we actually got a tighter execution bound, right? So these 1, 2, 3, 4, 5, the first two runs were from one normal distribution, and the second 5 runs were from the second normal distribution. And that was basically because the code had an if statement in it. And at the beginning, that if statement, depending on which way the if statement went, would put the execution time in one or the other of these execution time distributions. Okay, so that's that. We talked about real-time scheduling. There's lots of ways you can schedule tasks. We talked about periodic. Periodic scheduling is normally also preemptive. They're normally preemptive, meaning that tasks can be running and be put to sleep and let another task run, and then we'll come back to that task and finish it later. That's preemption. If you don't have preemption, that these scheduling becomes even harder without preemption. So you might think, well, preemption really complicates things. No, actually, preemption simplifies the scheduling algorithm. And then we talked about EDF scheduling and RMS scheduling. There's other ways to do this. What's even more complicated is if you are simultaneously adjusting the speed of the processor. Because sometimes you have extra time that you don't need, so you can slow things down and still meet all your deadlines and save some energy. But we didn't get to that, but there's some algorithms that do that as well. In this case, we assume everything's running at full speed. So when you schedule something, you get it done as quick as you can, and you move on to the next task. Okay, then we talked about bounds, which we already covered in the quiz. Partition scheduling, global scheduling for multiprocessors. Multiprocessors make scheduling much harder. There might be more up-to-date algorithms for that. Those are the best ones I could find for you guys. There might be better ones, but so we basically looked at a multiprocessor version of EDF and RMS. And then we have our own bounds, our tests, and that's it. So that's the whole semester. Any questions? Yes?
Can we expect questions like our quiz questions?
Yes, yeah, they'll be like that. I might have some fill-in-the-blank ones.
Oh, okay.
They might not all be a multiple choice. But yeah, I think that was pretty much everything. I think probably spent too much time on the interfacing stuff. Probably de-emphasize that next time a little bit. last semester, last spring, I had, the whole semester was just lectures. I didn't have any labs. So I had 2 additional major topics. One was queuing theory. You ever heard of that? Queuing theory is basically the theory of how things wait in lines, how long you can expect to wait in a line based on, the arrival rate and the service time. You can calculate the average length of the line. It's all statistics. But basically the idea with queuing theory is that as you increase the throughput, like the rate at which you request something to be done, generally the latency grows because you start to build up a line. You still get the task through eventually, and you still maintain the same rate, but you suffer in latency. It takes longer to get things done, right? So that's the basic idea behind queuing theory. And so the idea with that is, for example, like if you have a hard drive, right, on a computer, and you start making a lot of requests on it, it'll fulfill those requests at the same rate, but the time it takes to get stuff back from the hard drive will start to increase the more you backlog it, right? So, and that was, and the other topic was we went into Cmos Design. I talked about, I took some material from my old VLSI design course when I used to teach design for manufacturing. We used to actually design chips, ASICs. I talked about MOSFETs and CMOS logic gates, and we talked about delay, how delay works, and then transmission lines and capacitance, how you calculate capacitance in a chip. So that was basically all about, why chips are run at the speed they run at and what influences that. I got some pretty bad. I don't think that went over as well. The feedback I got was it was too many. The topics were too diverse, right? Wasn't as focused. I think this semester we kept a little bit more focused, right? So I hope you guys enjoyed the class. If you have any feedback that you want to share, feel free to send me an email. If you haven't taken 611, I'll see you in the fall. As you've probably imagined, this class also is designed to fit in with 313 as well. So we, took the platform design stuff from 313 and the Verilog stuff from 611 and combined them into control and interfacing, right, is the idea. This class will eventually, next time we teach this class, well, this is actually the last semester this class will exist because it's going to become 491. It's going to become the hardware capstone. And the goal is to eventually make it even more lab-oriented where we do more kind of project-based stuff. So this is probably the last time the course will be taught like this. So if you have any questions, also I will be out of town on Friday when you're taking the final. So if you have questions while you're taking it and you need a quick response, send a message to Phil, okay? I'll send him a copy ahead of time so he'll know what's on there. He'll be able to answer questions. Okay? All right, sounds good. Thank you. Have a great summer.